Hey there, SOS 232 folks. I hope that you're well. I hope that last module went swimmingly and that even though you went from the jump of single variables to two variables of bivariate analysis, things were hopefully, fingers crossed, not too terrible. We were still sort of going into the descriptive statistics and giving a very informal discussion on whether their relationship might be present. But now, this module, we're going to raise the stakes a little bit. And that's okay. I'm giving you this sort of, not necessarily warning, but a heads up that this module is going to be conceptually a little bit long, a little bit thorough, and very concept heavy. I think you all can do it. We're not going to go too deep into the woods, but we're going to see the trees a little bit for what they are. And so I urge you all, this module, to really pay attention to that time management component that I spoke about at the beginning of the course and that you get assessed every module on. Because this one's going to be important. I think my personal viewpoint is that the writing actually isn't much of an additional extra big piece of the puzzle. It's just that you're going to be thrown a lot of formal terms and really kind of formalizing a lot of the things we've already talked about through the first three modules into kind of a statistician's point of view. Again, this is the warning. Don't get overwhelmed by it. Take breaks, take breathers, hit up tutoring, hit up me, all those things, because we want to make sure, as a SOS 232 team, that we're good on this material and that you're good on this material. So as we're going to go through a lot, it's a long video. Make sure to take care of your own brain space. Don't get overwhelmed because we're going to do lots of examples. There's extra examples. And in fact, even some things that are, I would say, standard with this course, I'm going to expand a little bit. So you're actually going to get another attempt, an extra attempt on the quiz, this module. And you'll have more opportunities to really sort of build on what you've already done. We're just going to formalize it. You got this. I believe in you all 100%. And if you freak out, hit me up. Try to do so before deadlines. Early on, you know. All right, let's begin. We're going to go into module 4 now, which is analyzing relationships and comparing categories. In the PowerPoint presentation, we're going to continue to explore relationships between two variables through the crosstab or our contingency table. We're also going to formalize what it means to have statistical evidence that a relationship may exist between two variables as we formulate what we call our hypotheses. This module is going to be a bit concept heavy. Less heavy on the additional statistics. We're going to have some formalities, but for the most part, it's going to be just giving you a lot of terms again. You got this. Ask questions if you need it. Don't get overwhelmed. Give yourself that breathing room. But we're going to start going from, we're going to report some data to how do I sound like a statistician? And what does it actually mean to have some statistically significant evidence as well as making sure it aligns with some practically significant evidence as well. Again, we're going to be doing a lot of material, so we're going to sort of review on some bivariate statistics and beef it up to talk about association and confounding. We're going to talk about dependent variables and independent variables. We're also going to work on the alternative or research hypotheses as well as the null hypotheses and use those things on our propositions. We're also going to work on some tests of statistical significance, look at assumptions, population versus sample, this representative samples, response rates, the GSS sample, and also dig a little bit deeper on the chi-square test of statistical significance, running our crosstabs and chi-square and interpreting these things in a very sort of all-together write-up that I think you all already have done. You did this a lot in Module 3 and near the end. We're going to now up the ante just a little bit, but you got this. And if it's not positive enough, hopefully your brain doesn't get squashed. And if it does, hit me up. All right. Now, before we use a bivariate test, we got to set up our propositions. And what are propositions? These are basically just clear, objective statements considering the relationship between these two variables. It's basically, if you've ever had a philosophy class, or if you had like something where you make an argument, it's basically like an argument. You are trying to determine whether or not these relationships might exist between these variables. So for example, does perceived happiness relate to education level? Things like whether your social class impacts maybe your views on abortion, or your income level impacts your views on marijuana usage. All these things can measure these relationships and various components that we will learn to analyze through basically the back half of this course. Now, two variables, x and y, are considered to be associated or related if the value of one variable gives you information about the value of another variable. And for the rest of the course, we're going to basically compare these groups and determine whether an association exists by comparing the descriptive values to see if there are noticeable differences that exist with them. We'll often look into the changes in responses for one variable, like going for folks with a graduate degree to ones with less than high school education that was completed. Does that change your breakdown of another variable, like the percentages of not too happy? It looks like with this degree level, if you're not too happy, graduate about 9.8%, less than high school, 24.7%. So we may want to look into see on whether or not there may be an association between these two variables based on this response and the percentages associated with them. Now, warning, put the volume down because I'm a loud person. This is your warning. Association is not causation. There's also the old term that's called correlation, does not mean causation. Causation is basically something one thing causes the other. If we have an association between two variables and a relationship between two variables, or when we get to module 6, we can officially call them correlations, because that's supposed to be only just two numerical variables. We don't want to say one sort of variable causes the other, because, for example, makes sense, studying for a test can be connected, related, associated to scoring well on an exam. If you don't study, it doesn't mean you're going to fail. It doesn't cause your failure. And if you study 50 hours, it doesn't guarantee that you're going to make an A. So you can't, even if they're connected to each other, it doesn't mean whether you studied or not will cause a specific grade. It's more looking at the patterns and relationships that you may see based on the data, just like you would look at patterns and relationships brought on by the sociological imagination that you may have done in a sociology class, basically looking at these concrete examples and seeing if there's a theoretical pattern that can be formulated from them. Now, association is necessary for causation. If a relationship isn't present, there's no reason to believe that a causal cause and effect relationship could occur. If you don't see a pattern, why would we think that the pattern, if there's no pattern, then why would we think that a specific kind of pattern would exist? Associations can provide evidence for us to explore potential causal relationships that one thing causes another. Often researchers will use a designed experiment, like in biology or even psychology labs, to determine whether causation occurs. In survey research, we're only observing what the people respond to as. We're not telling them to do anything. We're not providing any catalysts to sort of cause something to occur. So it's really difficult to try to make a claim that causation is happening. We try to avoid that word of causal effects or causation necessarily. And we sort of just say, we're not going to be pretending that we are running the gears. We're just observing, picking up what's going on, and looking at these relationships, associations, and acknowledging that these patterns may exist. And if they want to try to provoke certain stuff, we can work on that through a think tank or whatever. So let's consider an example. It's been found that there's an association between ice cream sales in a town and a rate of violent crime. Does this evidence suggest that the ice cream purchases are increasing the rate of violent crime? Baskin Robbins. So does this mean that, I go grab a pint of Ben and Jerry's ice cream, and man, do I want to rob a bank after that? No. I'm not going to do something like that because I consumed ice cream. It would make sense that ice cream purchases are actually increasing the rate of violent crime. What's really probably going on is that there's what's called a confounding variable, we'll talk about in a second, with basically a background variable known as, maybe warm weather. When it's warmer, we eat more ice cream to keep cool. And actually, when it's warmer, violent crime seem to increase. Who wants to rob a TV from a home if you have to go in freezing weather after it? Am I right? In that situation, there's a background variable that's actually going and causing both of those things to increase without the two actually increasing each other. So we see that there's a pattern brought on by something else as opposed to a cause and effect relationship. A confounding variable is basically a variable that's related to both the explanatory and responses, so basically the two other variables, in such a way that the effects cannot be separated from each other. This is what I call a spurious relationship. Basically, we don't know, we don't think that those two other variables are connected to each other, but there's something in the background that may actually be saying that, oh, there's a pattern, there's an association, there's something going on. We just don't know why. The confounding variables actually will explain why the association doesn't, would occur. And it also helps show, especially with our example, why association does not imply causation, because we might be missing the bigger picture here. A nice example, breast cancer diagnosis rose by over 300% between 1973 and 1992. Was there a breast cancer epidemic? No. Actually, what happened was in 1976, mammograms were implemented in screening in 1976 because mammograms became a regular regimen for folks. They detected these things. They found the prevalence being basically because we were able to detect it and find it. And because it was found before it could get, hopefully, could be dealt with through treatment, and survival rates increased and all those things before it became worse. And so we don't want to necessarily claim one thing causes another, even if we see that there's a relationship that may be formed. Now, typically, we want to try to see whether response changes for one variable impacts the descriptive statistics for another. We may not want to say causation. We may not say that one thing causes the other. But just because we don't want to say that it causes the other, we can still see if one variable is associated with how another variable might vary. And the associations work in reverse too. So we say if an education level is associated with how happiness levels vary, we actually can go in reverse too. The happiness level is associated with how education levels vary. It's like X and Y are related, then that means that Y and X are related. Associations allow us to do that. Causations actually may not be. Typically, it's not. It's usually one thing impacts the other. So, for example, if I were to stub my toe, I might have a broken toe. However, if I have a broken toe, it doesn't mean that I actually, stubbed my toe on something. I could have had an issue with running and stress fracture, things like that. And so there are other reasons that this could occur, which leads into taking what we were talking about and turning it into what we call a proposition. So I say, one thing could impact you, or if you want to see if one thing is related to the other, we can put it in what we call symbolic form. And this little value here is what we call a tilde. This is basically y tilde x, or y sort of squiggly line x, y squiggle x. This tells us the same thing as saying is x associated with how y will vary. If y is changing among these values as x changes, then we think that y might be dependent on this in some capacity. We won't necessarily call it causal, but we'll say there might be some sort of relationship that this response on y, our dispositions, for example, this is focus of our analysis, might be impacted by these variables x. This variable, this y, this dependent variable, usually is a disposition on like what political party you are in, what your beliefs on abortion, marijuana, living with people outside of marriage, etc. All those attitudes, beliefs, behaviors, these are usually what it's going to, your title of your paper and basically what you're trying to research and the other variables that go along with it. So in this component, our dependent variable then wants something to explain it. We have these independent variables, x. The x marks the spot. It's basically the variable that is proposed being able to explain the differences in y. In survey research, it's usually properties. It can be other beliefs if we want to try to see if there's a relationship. These properties, these demographics or household characteristics, the researcher believes may account for the differences in y. It helps explain why the differences may occur. We're not saying it causes it, but we might see this is why, if these things are changing in x, this is maybe why these things are changing for the y variable. And when we're trying to assess whether these relationships exist, we need to set up what we call our null and alternative hypotheses. In general, a hypothesis is basically just a statement about a population using our propositions. The null hypothesis is a claim about a population parameter or something about the population that's initially assumed to be true. There are analyses. The null hypothesis is usually a statement something like there's no relationship between variables x and y. So there's no relationship between happiness and education level. It's a good sort of thing to keep in mind, is we always have in the back of our head that everything is on its own. There's no relationships. And our goal as a social science researcher is to find those relationships, just like we would as a sociologist. We're trying to find the patterns based on our concrete observations out there. So then we have what we know as our alternative or our research hypothesis. And usually null is like 0. So that's why I have an H sub 0. And the alternative is H sub A. It's the competing claim that we are researching to be true because we want to try to disprove the idea that nothing is connected to each other. Everything is sort of this nihilistic, things are just doing whatever. No, we think that society is interconnected. There are relationships involved. And so we want to try to determine Were those relationships, not everything is related, but there probably are relationships involved in some variables, in some responses. With our analysis, the alternative hypothesis is usually something like there's an association between variables x and y, or variable x is related to how variable y might vary. And for a good example, education level is associated with happiness. As opposed to saying there is no relationship, our goal is to try to prove that there is one. To evaluate the validity that associations exist, we do what we call a hypothesis test. And you can think of a hypothesis test as basically like going to a courtroom trial. In a trial, the jury runs on the idea that innocent until proven guilty. And so they need to decide between one of two possibilities. Either one, the person is innocent, or two, the person is guilty. And in the US courtroom, it's innocent until proven guilty. So we always begin with the assumption that someone is innocent. The prosecution will collect and present data for all available evidence to try to convince the jury to reject that original assumption and say, actually, there's so much evidence out there that I can't believe within any reasonable doubt that they are innocent anymore until we conclude that the person is guilty. If there's enough evidence, that's when we find someone guilty. But if there isn't, we find them not guilty. We don't say someone is innocent because it may be that they are guilty. We just didn't have enough evidence to prove that guilt was occurring. We sort of failed to reject that the person is innocent. So keep that in mind as we're going forward, is that really what we're trying to do is we go with the underlying belief that there is no relationships, and we're saying, all right, that could be the objective viewpoint. There isn't a relationship, but we think that something's going on. So we collected information, we got survey research, and we're trying to prove the relationship, the guilt exists. In summary, it's a claim basically of innocent, there's no relationships, or there's no relationship between these two variables. And in our analyses, it's basically guilty is the alternative, that we're guilty of our relationship. So keep that in mind for our summary. Our next step will be testing the propositions. So we want to know, how do we test our propositions, and what propositions, and what statistical tests do we use? Is your brain melted yet? That was a lot. Let's take a short break, pause it, try some of the practice questions, see if these things are starting to click. We did a lot in terms of concepts, so I want to make sure that those things make sense, feel okay, and from there, we'll go on to the next step. Skimming through. All right, let's go back. You ready? We'll test these propositions. So let's go into the idea of these bivariate statistics. The bivariate statistics allow us to test propositions. The criteria basically is y associated or related to x. Which bivariate statistics you use really will depend on the types of variables in your proposition. So the nice part is that we basically have breakdowns. Are they both of x and of y? Are they both numeric? Are they both categorical? Or is one numeric and the other categorical? If both of them are numeric, you do something that's called a correlation or a regression. We'll do that in Module 6. So we're basically going backwards. If I have one being numeric and the other being categorical, typically you might, for associations, you might go through the easy way of performing what we call a t-test or an ANOVA, and that'll be Module 5. But if we have two variables that are categorical, we typically will use a crosstab procedure using contingency tables and eventually a chi-square test. And that's what we did a little bit last module, and we will this module as well. Crosstabs, they're cool. They do a lot of stuff in terms of informing us about what's going on and what kind of information can be pulled from that, from our data and our summaries. So make sure when writing up your crosstabs, follow the rules of writing, check the Jamovi stuff. We're going to be doing these things in this lecture, but we have more opportunities for that as well. So if we have something that's where both X and Y are categorical, we usually will use the crosstab statistic for our analyses. The frequency distribution is really the only way to summarize this type of data. So once you overlay one frequency distribution on top of the other, they do the cross counts, compares where the cases are more represented in one category over another, and it gives us a sort of good idea of where these breakdowns might be. So let's try a practice problem to get comfortable with what's going on. So let's look at the GSS 2012 and look more closely at who's more likely to favor or oppose gun control measures through the following GSS question. Would you favor or oppose a law which would require a person to obtain a police permit, like concealed carry, something like that, before he or she buys a gun? So let's set up our proposition. And let's do this in more symbol forms, less paragraph form. You have to do both for this module. So let's make sure everything feels okay right now. Step one, the symbolic form. Basically, is that y tilde x basically telling us is y being base. Can we detect variability in y based on which values of x we got? So is gun control related or associated to our education level? We'll state our research and alternative hypotheses first. In a stats course, you might do them both side by side, and you may actually state the null first in terms of symbols. I'm not too worried about the order at this case if you had to write it out in terms of those things. But if I'm going to talk about this stuff, we usually will lead with the idea of what our research is about. Do we think that Americans with higher levels of education, that's maybe the real kicker, will be more likely to support stricter gun control measures because they may have read more on reports regarding gun violence? Always make sure to use the because statement and explain why you think this is happening. Don't just say, oh, this should be higher. Why do you think it should be higher? We all have experiences, and we're allowed to sort of pull into that without going to that personal I and just talk about it as a member of the scientific community. You may have read research articles or seen, news reports or something that comes from outside peer-reviewed sources that say these things and give us a logic behind our reasoning. We might be wrong. Our data might tell us something otherwise, but it's still meaningful to tell us what's really going on. Then we also want to state the null hypothesis and be open to the possibility that there's no relationship between X and Y. Stating the null hypothesis reinforces the researcher's objectivity and that they may let the data speak for itself. So there will be no difference based on education level with respect to Americans' position in gun control, or you might even say there may be no difference. Either one. It allows us to say, I'm trying to do this. I'm trying to claim that there is a research element, that I, as the researcher, understand what's going on, but I could be wrong. And I'm going to let that humility speak for itself in my null hypothesis, to acknowledge that I don't know everything, or that what I may have known before might have changed over time. We would lead into a crosstab from this point when we say gun control is based on a possibly education level. And we can look at the values that are provided in that crosstab. Usually we let the dependent variable, which we said before is maybe typically our properties, be aligned on the rows so we can read across by rows, where we let the independent variable, or the one that's explaining be aligned along the columns, and to always make sure we have the percentage by crosstabs in the columns totals. We want to look at the column percentages to see, based on what group we're in for our X variable, what the response percentages might be. We did this also in module 3, so keep in mind, go to module 4, check the short video on how to run crosstabs in Jamovi, and run these following rules, something like gun laws versus degree and percentage by column. You should get a crosstab that looks something like this. You can see for favors, percentages that go across among these groups. This should look fairly similar to what we've done before. And in this case, it looks like the highest percentage is 76%, the lowest percentage is 72% along the favored row. So that doesn't look like there's much of a difference among these. Maybe the null hypothesis can't be rejected. Maybe we don't have enough evidence. Maybe our research, or what our research beliefs were, might be flawed. It could be that we didn't have enough evidence, and that could be a thing. But I'm not gonna risk my integrity as a social science researcher to claim that there is an association when our data doesn't really speak of it. It'll lead into our tests of significance. All the things I'm saying, we're going to formalize into that, which allows our researcher to determine whether their findings are generalizable to the population. Basically, I got data. Does this actually mean what we're hoping for it to mean with our information? These tests of significance are often referred to as inferential statistics and can be explored through two different lenses. We look at maybe something with statistical significance, which is important, as well as practical significance, which is something that I think you all, as brilliant humans that you are, already have. The statistical significance will develop. The practical significance is basically, let's look at the information and trust our gut on this, or develop our gut instincts so we know what's going on. They allow us to answer these questions of how confident we can be that these relationships that we're observing in our sample data, our survey data, reflect something broader that's generalizable to the population. And that is a huge question. We're dealing with survey data. We need to make sure we are answering the right questions. So when do you use a test of statistical significance? The answer, which are going to lead into our assumptions, are only when you have what we call good data. Well, good data, that's really descriptive. We'll figure that out, and we'll explain some elements of good data that allows us to, that is basically sample data that's representative of our population. So we'll make a couple of distinctions. So one, population. Population is basically scientists, social scientists that are sort of interested in population. So most of us naturally already moved at level of analysis when inferring on the sample of GSS respondents in the US population at large. When the major values of science is building generalizations and theories about how the world works. So when you all started talking about these things in module 2 and module 3, based on your data, you are already saying, this is what we think the population looks like, based on only our survey research results. Now, we can't ever really truly survey everyone. It's just not practical. Time and money is of the essence. And once you have a huge population, claiming you can do that, not so much. So we usually want to draw a random sample. We hope, really we strive, when drawing this sample, that it represents a good cross-section of the population so we can, in fact, draw those generalizations about the population based on our sample. However, who gets collected and responds even can change from sample to sample, which is sometimes why our descriptive data might differ from year to year. You may have seen that your values and your percentages, if you used 2012 when you were supposed to use 2018 GSS, might have changed. It could be that views have changed, but it could just been we got different people between those 2 years. And so when we get those different samples, the compositions of their responses might differ as well. To evaluate whether the data is what we consider good data, be sure to always evaluate how the data was collected and whether the sample is representative of the population. Representative basically means it reflects more or less on the general characteristics of a population. The type of example that we collect, including how many people we sample, is important. To help understand this representative sample, I'm going to give you an example that one of my sociology professors at EKU gave me when I was one of you all fellow students. Think of a population like a stew. Stew, you got a collection of various groups of items. You got your potatoes, your carrots, maybe your protein, your corn, etc. You got a bunch of items, you put it in a pot, and you cook it up. And that's everything. To sample from our population would be akin to getting yourself a portion of that stew. A representative sample would be maybe like getting a bowl of the stew. If you got a big enough bowl, you're hungry, you want some food, that bowl should look like basically a mini form of that stew. Have roughly the same amount of potatoes and carrots and protein and corn, etc. It looks pretty much like the stew itself. So if I were to taste it, to try it, to evaluate how the stew is based on that bowl, I would think probably similar views would be pulled, whether I have the full stew or that small sample in a bowl form. When we have large samples, that makes it more likely we're going to have a representative population because those demographics, those components of especially populations, are more likely to get picked up. And we get something that is, especially for those rare events, we get breakdowns that look very similar to each other. When we start getting smaller samples, we run the risk of missing vital groups which represent the population. We could see maybe getting it from a smaller cup or like a thimble. It could look like a stew. It could look like the broth, for example. And hopefully, in a cup, it might actually still look fairly decent. It might have the same amount of, roughly the same amount of potatoes. It might have a little bit more corn than we wanted, or we might not have enough of the protein we were expecting. And we miss those key ingredients that sort of represent the dish as a whole. So ideally, to get that representative sample, we want to get a big old bowl of our population to properly analyze how good it is. When working with survey data, along with evaluating our sampling methods, it's important to quickly review also something called response rates. Response rates represent the number of people who received the survey or who were asked to participate who actually went ahead and completed the survey. So if I were to send it out to 1 million people and only 5 people responded, well, that's garbage. I want a good chunk of who I actually sent these things out. I made a very complex survey design and put a lot of time and money into these things. And I want folks to respond accordingly. Good response rates, there isn't a good or bad, but typically, based on experience, for survey researchers, a response rate between 60 and 80% may be thought to be pretty decent. If you were to get a response rate of 30 to 40%, so only about 3 or 4 out of every 10 people actually responded, there may be what we consider to be a response rate bias in reported findings. And we have response issues and missing people. If we have those missing people at such high levels, maybe specific groups are intentionally not responding. If we miss specific groups, then we're actually not getting the population in general. We don't want to have low response rates because that means we're not actually making folks count. And if we aren't making folks count, the policies that are being derived are leaving folks to the wayside. A biased sample all these things. The sample that over represents the demographics of one particular group of another and may underrepresent means this bias sample is not representative of the sample itself. Finding the sample, the things that we get from it, our descriptive statistics, our eventual claims of association, can't really and shouldn't be generalizable to the population. And in this case, we shouldn't be using tests of statistical significance to make generalizations. If our underlying assumptions that we have a representative population aren't met, that makes everything we use trash. I had a great sociology professor in grad school who was like, a lot of social science information, data, statistical analyses, it's garbage. I mean, it's profound and theoretical and expanding upon the universe and wrong. I love that because it was like full on critic. Don't go full on critic too much into the nihilistic, nothing matters, none of this stuff is good. But keep a watchful eye. Because unfortunately, social science is ripe with research and studies that use bad data that is unrepresentative of the population to make generalizations about your population. I hate to tell you all, but all those SurveyMonkey surveys you may have done in maybe other classes for your small assignments are probably trash. You got your friends to respond whenever it was convenient, and well, that's okay. If it was for a grade, you got to do what you got to do. But for research, especially when you're starting to try to promote knowledge, you want to make sure those things are represented correctly. So you want to have a level of organized skepticism. As a future social scientist, it's your responsibility to be constantly skeptical of the research that has come before your own work, as to improve on the research and study design to advance our knowledge and understanding of the world. So questions to always consider: is the survey data representative? What is the response rate? These things also lead into the validity and the replicability of our research. So like these things are also all mingled in and worthy for analysis. And if you're getting hired on as a social scientist to work on these questionnaire designs and survey research, having those questions makes better surveys. Critiquing these things, calling it out, make sure that we refine our questionnaire design so we actually get the responses and results that we're looking for. So it leads into the thing we say under our breath. Is the GSS data good data? There's much discussion, honestly, and debate whether the GSS data is in fact representative of the US population. There's a general consensus that the sampling design yields relatively good results, and the sample each year is by and large representing the US adult population. The response rates for any given year is typically between 72% and 82%, which is pretty solid for usual survey standards. You all have already done really great work on kind of calling out some of the issues with the questions and the validity and all these things. So honestly, keep it up. We can conclude, we'll go with the, worst case scenario, we'll go with the assumption that GSS is really good, relatively good data. Feel free to be a little skeptical because it's your responsibility as a social scientist to sort of understand that. If you're seeing that certain, crosstabs involving race or sex are providing breakdowns that from maybe other data, maybe economic data or something like that, that's much more, beyond surveys, maybe they're using tax records or something. If there are other resources that are saying, these are what the breakdown should look like, and you get data that doesn't look like that, it may just be the GSS got a little wonky this year. It's okay to critique that. For those who might be interested, check out the link, the overview of the General Social Survey Project from 2016. And it sort of talks about these things and assesses that level of issues and sampling methods that honestly go a little bit above and beyond what we're doing in this class, because it's something called sampling weight, but to accommodate for those issues we may have. But it has some usefulness. All right. Breathe in. Breathe out. Breathe in. Breathe out. Take that break. I talked about a lot in this next sort of bunch. And I think it's a lot to sort of process. If this is all you did, maybe on Monday, good. And if you have that Tuesday free, take that breather. Try these practice problems, the practice quiz questions, and feel fairly comfortable with what's going on. And maybe after that break, try the next piece. All right. Pass through, do. See, there's lots of practice quiz questions to get comfortable with things. All right, let's keep going. Testing for significance. Again, what statistical test should I be using, and how should we compare the practical significance and the statistical significance? Just reviewing what we talked about before, is gun control associated with education level, or do values of the different educational values levels, whatever, affect how gun control views may vary? We'll state our research and alternative hypotheses, whether they're higher levels of education or there will be no difference or there may be no difference going on. And we're performing our statistical analysis. We often want to examine our hypotheses from both a practical viewpoint as well as our statistical viewpoint. The practical significance viewpoint has us look at descriptive statistics and compare them to decipher whether meaningful differences exist. In a stats year course, I might talk about something called effect size. But for us, it's more just saying, I don't know, what is that? Was it Judge Judy or something? The KISS? Keep it simple, stupid. I don't know. I'm revealing my age a little bit. But honestly, the practical significance should always hold up. If we think there's an association relationship, we should be able to see it with our summary data pretty decently. The statistical significance viewpoint, though, actually goes into some very complex formulas and mathematical statistics that either you don't have to do by hand, or in this class, we got a computer to do the work for us. We'll use Jamovi, and it'll produce statistical outputs that help us assess whether these relationships make sense or there's enough statistical evidence to prove beyond reasonable doubt there's enough evidence to reject the null hypothesis. When we have large data sets like the GSS, we typically will require statistical significance to exist. But just because we have statistical significance, honestly, there's another hiccup. When you have a lot of data, sometimes differences that the statistical evidence may pick up are just because we have a lot of data. We also want to make sure that there's a practical difference as well, because if there isn't, then we may just have a lot of information. And that's why it's saying that there is differences when there may not be from a practical gut instinct point of view. We'll begin with practical significance because basically, honestly, we did that last module. Nothing new, to be honest. We're going to go ahead and we're going to interpret our crosstab results using the same sort of percent difference rule we did before. So pick the category you want as your dependent variable, the y variable as the row, and you look at maybe the largest and the smallest percentages to compare those two values and see on whether that difference is large enough to determine whether a practically significant relationship might exist. We can't reject the null hypothesis if there's basically no seeming relationship. If the highest and lowest percentage difference is less than maybe 8 percentage points, the relationship might be considered too close to call. There's not enough difference in the percentages to suggest a relationship overall. If we have something between 8 to 20 percentage points, there's probably a moderate relationship. There's a slight relationship, maybe even a strong one, depending on what our sample sizes are and what all the other components in place might be. But if I see that, then I'm probably pretty comfortable claiming that there is a relationship from a practical point of view. And if I'm seeing differences over 20 percentage points, I don't really have to have that sort of uncertainty in my gut, especially if I have a large enough data set. Because if you're seeing differences over 20 percentage point, that means there is a gap. There is a jump when you go from one category to another. And so we seem to have a pretty strong relationship that we can assess. So for example, our claim was that Americans with higher levels of education may be more likely to support stricter gun control measures because they may have read more on reports regarding gun violence. If I compare the percentage of the lowest one, so high school in favor, 72.8%, though folks with a graduate degree or more are at 76%. So that's the lowest versus the highest. The difference between those two, what is that difference? Oh, I'll just use our calculator. 76.0 minus 72.8, 3.2%. No shame in using a calculator in this class. And that's really the level that you're going to be required to do in terms of some highfalutin math, some basic computations like that. Now, given what we see, that's not a huge difference. It's less than 8%, right? So, like I mentioned before, eyeballing it doesn't look like there's a lot of differences among the groups. And in fact, the largest to the smallest is pretty small, pretty tiny, not a lot of information in terms of relationships. They may just be very separate from each other, that whether you're in favor or against gun laws may not be very impacted by your level of education. That's okay. So in this case, it looks like we would fail to reject the null hypothesis, and that there doesn't seem to be much of a relationship. All right. So that was practical significance. We did that in module 3, honestly. And that should feel like review from the previous module. So determine whether you have statistical significance. That asks the following question. Are these differences actually there in the population? Or did we accidentally get some weird situation where the people that we sampled, no matter how hopefully representative it would be, gives us this strange, incorrect relationship? In statistical significance, it will actually compare all the cells and tries to use complex mathematical formulas. Something that's called eventually chi-square we'll talk about. And it's related to that normal distribution we talked about way back in module 2. We won't do much with it, but it is related to it. And it determines whether the chance of luck is extremely low. The chi-square is our first major test of statistical significance, and subsequently should only be used when working with data that's representative of a population that's under investigation. These are using 2 categorical data variables. And this is a test of significance when we use crosstab data. We'll try to determine whether or not we can be statistically comfortable in generalizing our findings we observe in our crosstab, our sample, to the population as a whole. The chi-square uses these observed and expected values and has this formula. I'm going to put it there. I ain't going to talk about it any more than that, because I think conceptually it's good to know. And these formulas are going to melt the brain more than it probably has already in this module. And that's okay. We're going to just consider this chi-square as basically a statistic, a value that summarizes all the information about our cells into a value that helps determine whether or not we might have a relationship between these two variables. So now we just got to learn how to set up our chi-square test and interpret our results. This requires that we talk about setting what we call our significance levels. When using tests of significance, even before using chi-square, we need to know our level of significance so we can determine whether or not we can reject our null hypothesis and determine whether a relationship between these two variables are statistically significant. 3 levels of significance that we basically run with is that there's no magical significance level, to be honest. Ones that you typically will see 5%, 10%, and 1%. In decimal form, maybe 0.05, 1% would be 0.01, 10% would be 0.10. These are ones that you typically will see in research. There may be even ones where it's like the 0.1%, and that's really, really fancy. We won't deal with that too much right now. The one thing you could never really want to do is test at the 0% significance level, where we have, this would lead to basically never concluding that you have statistical significance. And that's because we always have error. These significance values in general can be considered to be our error rates. And we'll talk about that a little bit more in the next slide. When evaluating our data, our level of significance can be compared using a p-value as well. When performing our statistical significance, we're going to continue to get something called p-value or probability level. This value is used to test what are the chances of incorrectly concluding that two variables are associated with each other based on the data we sampled. Should always be between 0, oh no, small hiccup, and 1. Sorry about that. And this is, when I say incorrectly concluding the two variables are associated, this is basically saying, based on our data we had as a sample, what's the chances of claiming something is associated when in fact the reality is that they're not, and we just got a weird sample. Our conclusion, whether we reject the null hypothesis or fail to reject the null hypothesis, we have in a relationship or we can't detect one, will be based on whether or not our p-value is less than or equal to our significance level. So whatever our significance level is, 0.05, 0.01, 0.10, if I get a p-value that's less than that or equal to it, I will end up rejecting it and claiming, in fact, that we have a relationship. There is an association. If it's too big, if our p-value is bigger than that significance level, we just don't have the evidence. It's not enough evidence provided. There may be one, but we just didn't find it based on the sample we collected. It wasn't good enough. So summarize, a significance level of 5% significance level is basically saying if no relationship actually exists, so that's what's really true about the population, we would have been unlucky 5% of the time with our data collection. And this sample that we got would have made us incorrectly conclude the relationship exists. So while our data might have, we call it p-value really small, and we reject this 5% significance level, the only reason it happened is that we were sort of unlucky with our sample and got one that wasn't maybe as representative, which meant that these values was determined to be just dumb luck. Not that a real association existed, but just that when we sampled, we got folks that gave us that value on accident. Basically, we run the risk of not, that's what happens when we run the risk of not getting the whole population, But that's not typically possible. To be unlucky 5% of the time is not a huge deal. It's not the worst. It's not maybe great, but it's not the worst. 1 out of every 20 times, if we were to go into the field, collect your data, if like run it like a simulation of the matrix, about 1 out of every 20, roughly, would have produced this. If there was no relationship, no association, actually, our data collection would have produced that on accident. It's also why you can't have 0%, because there's always a chance of screwing up if we were to make that conclusion. So we want something bigger than 0%, but 5% is fine. We also have the 1% significance level, and the goal for statistical significance for 5%. So our goal then would be getting a p-value that's less than or equal to 0.05. We also have a 1% significance level where there's less of a chance of making this error compared to the 5% significance level. I will say this, and I won't talk about it too much, but there is why you don't want something super low is that the smaller your value, the bigger chance there is to fail to detect a relationship that one actually does exist. So we don't want to go too small because we accidentally might miss relationships that are there just because the data we collected. The goal, if I use a 1% significance level, is trying to get a p-value that's less than or equal to 0.01. The 10% confidence significance level, my apologies, a few typos here and there, my bad. Fixed. The 10% significance level, greater chance of making this error compared to the 5% significance level. So you could have more of a chance of accidentally claiming relationships exist when they don't. But there is a smaller chance of messing up and failing to detect that association when one actually exists. In that goal, we want something that's less than or equal to 0.10. Whew! Your brain melted yet? Mine is. Take a breather, take a pause, not quiz questions yet, but then we're going to go into a practice problem and expand on everything we just covered to examine this relationship. Just like we did before, we're going to set up a proposition of gun control and does education level matter in explaining one's position in gun control. Put it in symbolic form. Why gun control tilde education level? State your research hypothesis. We think that Americans with higher levels of education will be more likely to support stricter gun control measures because they may have read more on reports regarding gun violence. State your null hypothesis. There'll be no difference based on education level with respect to Americans' positions on gun control, or there may be one, maybe no difference. All right, now there's one more step. Setting out your propositions. We're going to expand and now set at your level of significance. We'll start at the 5% level of significance, which means you'll be using a p-value of 0.05 to determine whether your proposition is statistically significant. And in this course, if you use 5% all the way through, full credit, no problem. I don't have an issue with that. If you want to expand to 10% or 1%, I'm here for it. I'm happy you're going to do that challenge, but I'm not going to require it too heavily. Now let's go to the next step. We'll test our propositions. We kept asking this question of what statistical tests we can use. Now, given both gun control and education level are categorical variables, we can use that crosstab and chi-square to test the relationship. We finally have our answer. As always, be sure to review the short Jamovi video on how to run crosstabs and now chi-square in Jamovi to be sure to follow the above rules. This time, ask Jamovi to also give you your chi-square results. It should give it to you automatically, but if not, make sure that value is checked. You'll get something like the following when you follow these rules for setting your crosstabs or contingency tables. And you should look something very similar, nothing that you haven't done before, but you'll also have your chi-square results. Gives you your chi-square value, the degrees of freedom, and a p-value associated with your sample size of 1,283. All right, so now how do I interpret these results? There are three values to read when you're interpreting your chi-square results. First is the value of your chi-square statistic. In this case, just basically what Jamovi punched out from that formula that I told you to, we're going to wave our hands, say hello, wave goodbye, and worry on how the computer will output it for us. This value, this sort of chi-square, looks like an x square. If I use a chi, chi hyphen sq, that's fine too. The value of 0.957. This df is called the degrees of freedom. It's basically a measure of how big the cross table is. It's a good measure. The bigger the degrees of freedom, the bigger the cross table probably would be. In our case, the degrees of freedom is 4. In a statsier term, this chi-square statistic and these values that we're getting from are very much determined on the degrees of freedom. And there's a mathematical formula behind it. We'll stick with our little reasonable layperson's understanding and go from there. P, or the p-value, is really actually the most important number we're going to need to making our decision. This p tells us the probability that our relationships can't be given over to chance occurrences brought on by who was sampled by the GSS, and basically whether or not something is statistically significant. This p-value is really big. Oops. So if I were to put this in parentheses, I'd have chi-square is 0.957, 4 degrees of freedom, p-value equal to 0.916. And this is the next part that's really, really mathy. I need you to help me, folks, because this is hard. 0.914 and 0.05. Which one of these is bigger? On some Dora Explorer. That's right. 914 10,000ths, or 0.914, is bigger than 0.05. That p-value is bigger than your significance level. So that means this relationship fails to be statistically significant at the 5% significance level. Womp womp. We don't seem to see that there's a relationship, statistically speaking. And not surprising, though, you already looked at the contingency table and you saw that from a practical point of view. Ideally, we want the practical significance, whether there is a relationship or not, to coincide with the statistical significance. Now, it'll give you this number typically, but sometimes our p-value will show up as this sort of less than 0.001. What that means is the p-value is actually really small, less than 1/1000th. If you see a p-value reported as such, just report it as p is less than 0.001, and feel free to easily conclude that we have a statistically significant relationship. I would say it's very rare for anyone to not feel comfortable being wrong less than that. So now, as we're nearing the end, how do I put it all together? Both the statistical and practical significance to write up our conclusions. To write up the results, we did our proposition statement. We're basically going to do the same thing, but now we're going to, as before, we do not include the null hypothesis in our write-ups. That's sort of the background knowing. We're now going to add a report of statistical significance as well. So put it all together. Does education level matter in explaining one's position on gun control? Americans with higher levels of education may be more likely to support stricter gun control measures because they may have read more on reports regarding gun violence. Comparing percentages show that those in favor of gun control laws are highest among those with a graduate degree at 76%, in comparison to those who finished only high school at 72.8%. This 3.2% difference, based on the percentage difference rule, does not suggest that there is a relationship between education level and opinions on gun control. Furthermore, this relationship also failed to be statistically significant. I provide the chi-square value, the degrees of freedom, p-value. While these findings report on 2012 data, it'd be interesting to now look at this relationship in 2025, given that how we depict gun control and gun use in our country. Remember, always end with directions for future research to continue the academic world. When writing the research, review the rules of writing research in this module and all others to follow, and reporting chi-square values. You'll need those tools on reporting the statistical significance when writing up your findings to do well in your blog post and homework assignment. Remember to learn how to get to chi-square results and test statistical significance in Jamovi, General Social Survey data. Watch the Jamovi short video. You will need those tools, just like before, I'm running this stuff. There's going to be some practice questions ahead. And I bet you feel a little bit exhausted. That's okay. Take that break. Take the rest of the day off if you need to. As long as it's not Wednesday you're watching this. Before going forward, and try to test your knowledge, make sure things make sense. Take that break, that breather, because you just absorbed a whole lot. The next goal is to go ahead and let it sink in a little bit, and then try some practice with your blog posts, with your homework assignments, quiz, so on. As a final note, this is a lot of information. It's kind of the biggest stuff you will have done statistically. And for a lot of you all, anxiety levels are riding. Take that breather. Know that you are worth way more than number crunching. And the write-ups, check it out. We didn't really do much in terms of write-ups that go beyond anything that we did at the end of Module 3. So while there was a lot of material, there wasn't a lot of changes going from Module 3 contingency table analysis to Module 4. The only difference is we'd start formalizing a lot of stuff, which feels very heavy. There'll be an additional practice video with some more questions as well as your Jamovi to get comfortable. Read through all the things because honestly, that's how you're going to do well. Keep going, folks. It's going to be fine. Going to be great. And most importantly, take care. You got this.